until next session to submit the homework. And regarding the syllabus, I send the syllabus through the Blackboard, so everybody should receive the syllabus, whether they are attending the class or not. So is there anybody who did not receive the syllabus yet? If you didn't receive the syllabus, you need to check your email with the IT department. Anyway, for this course, you can just search the course title in the CityTech website, and you can access to the syllabus as well. Let me see what's going
Professor,
on.
is your email the MKHODAP 000?
Yes.
Yeah, because I sent a few emails like last week and I didn't get
But
any
I
response.
didn't receive. Eric, is that you?
No, it's Steven.
Is it Steven? So I didn't receive any email from you. I regularly check my email, but it's at City Mail at.
I'm looking at it right now. I'm looking at the email that I sent you, and I sent it on the 6th.
Could you reply to one of them right now?
Yeah.
In case, I don't know, maybe I miss it, but usually I.
All right, I just sent it right now.
Check my email. I still didn't receive anything. Still no email. So here is my email. I'm typing it in chat. Just double check.
Yeah, that's the email I sent it to.
So, James, what do you mean by having homework file?
Professor.
Let me ask James, and then we'll go back to you.
So when I go to the content and like the Blackboard, when I click on the homework, it doesn't like give me instructions as to like what I'm supposed to do. It just says the due date.
Yes, but previously when I go through the syllabus, I told everyone that in this syllabus there is a table in. Let me share it one more time quickly. So if you remember from previous session, we said there is a table at the end of the syllabus section. It says, for example, week 1, what topic is covered, and if the chapter 1 finished, which is the pages from the book that you need to go through, and this is the homework related to the chapter 1. So these are questions that you need to answer. Today we are going to teach about chapter 2, and when the chapter 2 is finished, here is the pages mentioned, and then from chapter 2, here is the number of homework that you need to do for the next session. Is it clear? Okay. And I sent the syllabus at the beginning of the previous session to your email. Luis, what is your question?
Yeah, I never received that email. I was looking for it and I never found it, so I didn't have any idea about the homework until today.
So for today, I mentioned. So if this is the course number that you have, it's EET1122. If you search for your course even in the CCNY CityTech website, you will end up having this syllabus. It's also there. And I sent you also through the email. So I don't know, Luis, if you were present previous session.
I was.
Yes, you were present, but it's the point that what I'm saying I'm sent you the syllabus and I'm going through the syllabus. if you didn't receive it, it's better to talk at that time, okay?
Okay.
Just in order to figure it out the way for you or something like that. But it's okay for today's session if because some of you has still like wasn't clear for some of you what to do for homework and some of you are not ready. I will give you time until next week to submit the homework for chapter 1. What else? No, my email that you have is at CityMail, not CityTech. Okay, let me start the attendance for,
Wait, Professor, it's I just sent you an email. So you said City Mail?
yes.
All right, because yeah, I had just sent you one. I don't know if you might have received it.
I still didn't receive anything on my CityMail, but I can double check my email to see if this is the problem.
Yeah, I was gonna say that also.
Let me check. Please use also your CityTech mail when you sending email, so it doesn't go anywhere else. In my spam, no.
Yeah, it's so weird. Cause I just sent it to
Uh,
that same exact email.
I will double check with the IT whether my email is up to date and is fine,
Okay.
or you can also do it on your end as well. Okay, for today, let's start with the attendance first. Jose? Steven?
Here.
Eric?
Here.
Luis?
I'm here.
Javier? Thanks. Wayland? Thank you. Simon?
Here.
Saima?
Here.
Leon?
Here.
Anthony?
Here.
Edmund? Ryan? Kosela?
I'm here.
Sareni? Thank you.
Here.
Lithbeth? Roshan?
Here.
Dariel?
I'm here, Professor.
Cornell? Cornell? James?
Here.
Is there anybody I didn't mention his or her name? Okay. So just give me a couple of minutes to pull up the slides for chapter 2. Take me sometimes to upload the PowerPoint. Sorry for that. Meanwhile, do you have any question? Okay, I guess everyone now with access to see my screen.
Professor?
Yes. Question? Hello? Okay, let's start with chapter 2. In this chapter, we are going to cover a topic regarding the voltage and the current. Before starting, talk about the voltage and the current. We want to more know about the basic atomic structure of the conductors like copper or aluminum, and know why they are using so much in this field, and then understanding the voltage concept and how this terminal voltage is defined for some equipment like a battery or other type of voltage sources that we have. Then we're also going to learn how the current is established in a circuit, how the magnitude of the current is affected by the charge that are flowing into the circuit, and then become familiar with the factors that can affect the terminal voltage of the battery and how long a battery can work and produce power. And at the end, we are going to learn how to apply voltmeter and meter to measure the voltage and the current of the network. So for the voltage, we usually is a term that we use regularly. For example, you know that the plug that you have at your home, it provides 120 volt voltage at its terminal, and most of the equipment that you have at home working with the 120 volt voltage. So with the current, it's usually that people are less familiar with the current, but usually you know it from the fuses if you have at home, or if you have any specific equipment or devices that need a specific amount of current to be supported. And let's start the basic structure of the atoms and electrons. Let's start with the pictures like this one, which shows the hydrogen and the helium atoms. As you will see in hydrogen, you have proton and nucleus in the middle, which is the core of the atom, and you have one free electron that is orbiting around the core in a orbital path. And then in helium atom, as you will see, there are two protons, two nucleon, and two electrons that are going around the atom. If you remember from the, also just going to remind you something from physics or chemistry, is that whenever we have like more proton in the core, so they have like more strong power over the electron. Electron is less free than the time that we have less proton in the core. And then when we have one single electron far away from the core, it's this one called as a free electron, that this one can move from one point to another layer. Usually electrons going to go from outer layer. So if we consider the copper, which is the most commonly used metal in the electronic and electrical industry, it has 29 electrons in orbit around the nucleus. With these 29 electrons, they are appear in different shell, that at the fourth shell there is a free electron, as you will see here. These 29 electrons are arranged like this. In the fourth shell, there is one electron. This one is far away from the core, and this one can freely move between another atom of the copper. So having this electron at the outer shell make the copper become a very like a material which can conduct and let the electron move through it and make it a good conductor in this industry. And here it shows the amount of power through the radius far away from the, like when you have two Q1 and Q2 as a electrical charge, there will be a forces between them that these forces has inverse proportional to the root square of the distance. So if you have electron and proton far away from each other, the distance is in here. So when the distance is bigger, the amount of force or the amount of kind of, let's consider it force that can keep the electron at its shells will be very small. So that make the electron to run freely. When the electron move from, like when you get an electron out from an atom, then a positive ion is created and simply a source of a voltage established by creating a separation between the positive and the negative charge. So if you have accumulation of positive charge in one side, accumulation of negative size in another side, between them you can create a voltage. So here it shows the amount of voltage between the two charges. If the two charges are small, the amount of voltage that can be created, considering the distance is the same in all of them. You have a 1 volt of voltage, and you need to kind of, if you have a 1 coulomb charge in here, you need to do 1 joules of energy to move this charge from this point to the other point. If the charges get bigger, then the amount of voltage that you have in here will be bigger. And then the amount of work that you need to do is also bigger. If you make it more, so if you have more accumulation of the charges, so the amount of voltage that you can create is also bigger. So when we talk also, let's clear this one is also very important in some of the homework or example, you need to also know this one. 1 coulomb of charge, it's associated with this number of electron. This one is 10 power of 18. Just make it correct. I have to correct it also in here. It's actually 10 power of 18. You have it also in the book. So when we say 1 coulomb of charge, we means actually this number of electrons. It's a big number, but this is the number of electrons that is considered as a 1 coulomb of charge. And as we said, 1 joule of energy is used to move the negative charge of 1 coulomb from one point to another point.
Professor, can you go back a slide, please?
This one?
Yeah, that one right there. All right, thank you.
So all the topic that I'm covering in here, you have it in the book. So even the text is from the book.
Okay, thank you.
Just to let you know. And here it says the difference, as an example, the difference of the potential between 2 points if it's considered 4 volts, or the potential between the point and the ground is 12 volts, or whatever case that we are talking is actually the amount of work that you need to do from moving 1 coulomb of charge from point negative point to the positive point. So far we learned about that if we have accumulation of charges between the 2 points, there will between them there will be a voltage. So how we define current? As we said, these electrons are moving through the conductor. So when the electrons are moving through the conductor, if you put a plate in the middle of the wire, like a surface in here, and then you start counting the number of electrons that goes through this surface in a specific amount of time. For example, for 10 seconds, I want to see how many electrons are moving. Or for 1 second, how many electrons are moving through this plate. This number, the amount of electron divided by the time, the specific time that you have, give you an index which is called current. So the rate of electron moving through the space is called current. If we have higher current, it means that high number of electrons are moving. If we have less current, it means electrons are moving in a small space and a small number of electrons are moving through the space that we have. So here is another example. If I have accumulation of electron in one side and accumulation of positive charges or ions, positive ions in another side, as we know, between them, there will be a voltage or electric potential. And now, if we could create a path between these two, like connecting all the way through the wire, then there will be a flow of electron from where the amount of electrons are high to where the amount of electrons are low. So then we have the flow of electrons like this. And as we said, flow of electrons actually called the current. And if you have any bulb in between, like for example, this is your battery, accumulation of positive charges, negative charges, and electrons start to flowing because I have a closed path in here. And then if you put a bulb in between, because electrons are moving through here, they will light up the bulb. So the unit that we have for the current is ampere, which is actually the coulomb per second, and it's in the honor of effort of Andre Ampere that do the study in electricity in motion. So usually we can say as a summary that when we apply voltage to a system, there is a pressure to set the system in motion, and the current is reaction to that pressure. So whenever we have applied voltage to a system, if we have a closed path or a complete circuit, then we have flow of electron, which is actually having the current. So it's important to know that the amount of current is also very important. So experimental results reveal that the human body is reacted to the current only even in the few milliampere. So when you're working with anywhere that there is a voltage, so there is a possibility for current. So you have to be careful of the amount of current and the voltage that you are dealing with, because even a small amount of current can cause damage. So as we said, here the 10 milliampere even, you may consider it as a very small current, but this amount of current can be also dangerous for human body. So another term that we are going to talk about it is the term DC voltage. So in the DC voltage, we have always the amount of, so this is the symbol that we use, and we show it with E. And when it's a DC voltage source, it's usually, no matter what's going on, it's always give you the 12 volt voltage at the output, and this value does not change. So voltage sources can be divided into 3 basic types. They can be batteries, they can be generators, or they can be power supplies. So with the batteries, you know, chemical battery or some sort of also solar energy considered in this category. Generator like electromechanicals, when they have like a turbine or they have another part that create forces to move the shaft of a motor, or like shaft of a machine, and then produce electricity at the terminal. So we consider this one as a generator. Power supplies are like kind of devices that connected to the plug of the buildings or anywhere that we have. They use, so just to make it clear, the voltage that we have in our system at homes or at office or whenever else are AC. They are sinusoidal and they're changing from positive to negative, and their value is changing over time. You can consider give the AC signal to the rectifier, which is a power electronic devices, work based on some switches, some diodes and capacitor, and create this DC constant value of the voltage for you at the output. So another source of voltage or power supply. For the battery, we have 2 types of battery. They are primary cell and they are secondary cell. In primary cell, they are not rechargeable. So when it's depleted, it's over. Like a small battery that you use for toy or like for a lamp or anywhere else, that when it is a voltage, when they depleted, you cannot use them anymore. You have to dispose it. But secondary cell are type of battery that you can charge them and use them again. Like for example, the battery that you have for your phone. When it's depleted, you can plug the phone to the outlet and get it charged, or the battery that you have in your laptop. When it's kind of depleted, you can recharge it again. This type of secondary cell can be classified based on the material or the chemistry they use inside the battery. They can be lead acid, nickel metal hydride, or lithium ion. So here we're just going to go through different type of battery, just to see the figures, how they look like, or if there is any specific things about them. So here in the these are like alkaline primary cell, which means if they depleted, you cannot charge them anymore. And this one shows the structure and some components of the characteristic inside the battery. And here we have battery in different size and different ampere hour. So it just makes something clear in here. We will go through it later and I will describe it in more detail. But as you will see, for each of these battery, we have one term, which is the voltage, the amount of voltage that can be appear between the terminal. And you have also the term ampere hour or milliampere hour. So it's ampere hour is the amount of current that a battery can provide during an hour. So when it's 52 ampere hour, it means it can provide 52 amp, up to 52 amp during 1 hour. If you increase the amount of hour, like to 2 hours, you reduce the amount of current that you can use. So multiplication of time and the current should be always 52. If you increase the time, you reduce the amount of current. If you increase the current, you can use this battery for a smaller amount of time. And it's also recommended that not to use battery more than, like, for example, 52 amp that is here. Don't use it for 100 amps, for example. It will damage the battery. So it's another kind of primary battery, which is the lithium primary battery. As you will see here, we have different sizes, different shapes. All of them provide 3-volt voltage, but they have different current capability. So as you see, when they are getting bigger and bigger in size, they can provide more amount of current in a specific amount of time. So this one is an example of lead acid battery. You can see different parts of the battery in here, and the amount of voltage that this battery can provide from negative terminal and the positive terminal that is in here is 12.6. It's like a car battery. Another type of rechargeable battery is nickel metal hydride that you will see in here. The amount of voltage that they can provide is 2.2 volt. This one can provide 7.2. And as you will see from this, when you increase the size, you also increase the current capability. And this one is an example of solar that you put in here, like in a roof of a building, and based on the amount of sun that they absorb, they can produce electricity in here, and this electricity can be used at home for fridge, TV, outlet, or whatever equipment, or also it can charge the battery. So during the daylight, when there is a sun, this solar will produce power. Some of this power is used by the appliances. The rest can be saved in a battery. And when during nighttime, when we don't have a sunlight and there is no source for producing the energy, we will use the energy that is saved in this battery. Any questions so far? So, and as we said, another source of voltage is the generator that you apply torque, or there will be a turbine or any mechanical system that can rotate the shaft of a generator, and then at the output of the generator, we will have the electricity. So as we know, and as you may guess, the amount of power, voltage and the current that can produce by the generator is much higher than what can be produced by battery. So here is an example of a generator. You apply the forces in here, anything that can rotate this shaft, and then based on the electromagnetic field that created in here and the amount of wire that we have in here, at the terminal of this machine, there will be an electricity, which is the voltage, and you can connect it to any appliances or to the home plug, so to use this electricity. This one is an example of power supply. You can connect it to the outlet of the home or office or the lab when you have 120 volt AC signal. This one inside has some electronic component like switch and switches and the diode, and then convert this electricity from AC to DC, and then you can, with these knobs, you can adjust the amount of current or the amount of voltage that you want. For example, this power supply can provide voltage from 0 to 60 volt, and the amount of current that it can also provide is from 0 to 1.5 ampere. So depends on what you have in your circuit. Usually this power supply used when you have a special circuit like electronic or electric circuit, and you want a specific amount of voltage, like for example 10 volts, and then you will apply, with this knob you will set the voltage to 10 volts, and then you, from these ports that you have in here, positive and negative, you will connect some dragon wire, and then from alligator wire, and then from them you can get the voltage and connect it to your circuit whenever you need. So if you look at in this device in here, there is also a green port in here, which on top of it is mentioned GND. GND is the abbreviation for ground, and usually the ground point has 0 volts. Now the way that you can connect is that you can connect the ground through a jumper wire to the negative, and then you have 10 volt from the positive, because now the negative point and the ground are connected, and from the red port you can get positive 10 volt voltage. This is the ground, so you have a voltage source that is connected from one side to 0 and from the other side to the positive 10 volts. This is another example. If you connect positive port to the ground, and from the negative one you have negative 15 volts, then the description for this circuit is a circuit like this. You have ground, you have a negative point, and you have a voltage source that is reverse than this one. So the bigger part is top and the smaller part is in the bottom. But when you have positive one connected to the ground and have the voltage at the negative terminal, then the positive part, which is the bigger part, is connected to ground. The smaller part, which is the negative one, is connected to a point that has negative 15 volts in here. If you just connect the ground to the green point to the ground, leave it alone, and then you have a voltage of positive 5 volt between the positive and the negative terminal. This one can be resembled by this, a voltage source between positive and negative point. And in this case, we call it a floating circuit. When you don't have any reference point for the 0 voltage, your circuit is floating. And then beside the voltage source that we discussed, we also have the fuel cell, that these fuel cells are like some sort of a small stationary power plant that they can, that they are using in this power plant. They sometimes use in transportation for the train or the buses. And then they have some other application like the space shuttles and so on. So this is show the components of the fuel cell in here. As you will see, this is the basic structure or the schematic for the fuel cell. From one side, you bring hydrogen, and from the other side, you bring oxygen. There will be a chemical reaction in here, and then based on this chemical reaction that happened, you will have the voltage that is created. As we know, in the terminal, you can have a potential similar to the other battery. There will be a positive point, there will be a negative point, and then between them, there will be a potential. And if you connect a lamp into a battery, you can let it on because there will be a flow of current. But here, if you look also, when the hydrogen and oxygen are combined, they produce water, because the water is H2O. And also because the chemical reaction is a process that produces heat, we have both water and heat created in here. And this is an example of fuel cell used in electric machine. So usually the type of electric machine working based on this structure, that when the motor is going to stop, the motor acts as a generator and produce electricity, that this electricity can go back and save into the fuel cell. And then in some uphill cases, when you need to have more power to push the car through the hill, instead of using gas, they use this electric energy that's coming from the fuel cell. They release the energy and let the car go. So another topic, as we discussed, is the ampere hour rating of a battery. And as you noticed from the other slides that we were going through, besides the voltage level of the battery, there was also a terms of ampere hour that shows you the amount of current that a battery can provide for a specific amount of time. And now we are going to see that if you remember, I said that if you increase the current, you can damage to the battery. There is also a case that depends on the amount of current that you get from the battery, you can have affected the life of the battery. So here we are going to see the life of a battery is related to what parameter and how they can affect it. So let's consider this example that says a battery with an ampere hour rating of 100 can supply a current of 10 ampere for 10 hours. As I said, the multiplication of current and time should be equal to ampere hour. So if I use 10 ampere, then it can provide 10 hours. If I use 100 ampere current, then it, based on the understanding that we have, it needs to provide 1 hour of current, because 100 ampere and 1 hour is equal to 100. But in reality is that when you increase the current to a current next to an ampere hour, then instead of 1 hour, the battery will work actually for 20 minutes, because it's a high amount of current. And battery, when you run the battery at this amount of current, it's affect the performance of the battery, and it cannot work more than 20 minutes. So when you have a battery, it's better to run the battery in a smaller amount of current. Usually half a value of dimension for the ampere. So here it shows you the life, like kind of the ampere hour rating or the capacity versus the amount of current that you get from a battery. So if it's a 20-hour ampere hour battery, these are the amount of current that you can run. So if you wanna let it, for example, see what is this ampere hour rating, if you run with the 25 milliampere, it's provided with the 18 ampere hour. If you run it with 100, it's actually like 17. If you run it with 200, it's actually 15. So as you will see, when you increase the amount of current, you actually reducing the ampere hour rating, or it cannot work as it's supposed to be. Like, it cannot provide the rated value because you are going to use high amounts of current. So it's very important topic that when you have a battery, don't run it for a high amount of current. Usually, in order to keep the battery near to the state of keep the life of the battery for let the battery to be healthy for a longer time, they usually keep the amount of current in a small value, but let it run for a longer time. The other factor that can affect the performance of the battery is the temperature. So either if the temperature is high, more than some amount of current, the capacity will reduce, Also, if the temperature is going below some value, like in the freezing point or below that, we also have degradation in the performance of battery. So it's better to have the battery in room temperature. Below room temperature, we have decrease in the battery capacity. Above the room temperature, also we have degradation in battery performance. So when your battery is going to work in a hot summer, there will be a degradation in power output. If it's going to work on the cold winter time, it's also there is a degradation in the performance of battery. It's important so we have to let the battery run during this time, but important things is to know when you know this factor that affected the battery, when you want to design a battery system that's going to work in a summertime or it's going to work in a winter time or both, you have to consider some extra capacity, or you have to size it in a way that you consider this factor that reducing the performance of the battery. So here is also the amount of discharge time that they have and the amount of terminal impact on a terminal voltage. So if you look at this graph, if the terminal voltage is 1.5 over time, when it discharges during different amount of like if it's run for a longer time, these voltages is reduced from 1.5 to 0.9. So the terminal of the voltage of the battery is no longer at 1.5. It degrades over time. Depends on the amount of current that you are taking. When you're taking so much current, it degrades very fast. If you use the gradual current or the medium current, it's also degrade gradually. And if you use it very smaller amount of current, it's this voltage degradation happen over time. For example, if you want to work around, for example, 200 hours, as you will see in here, if you run the battery with 100 milliampere, before 200, your voltage dropped to 0.9. But if you, for example, up to 1 is fine, but if you run it with the 50, it degrades voltage very fast. But if you run it with 25 milliampere, after 200, you have voltage at 1.3. So yes, battery can still work fine, but the problem is that if you go voltage, for example, below 1, or depends on your system, maybe protection devices activated, disconnect your system, and the battery performance is not good again for this system. So usually when we have like a battery voltage of 1.5, we want this battery work within 1.5 or within the limit. Like for example, work between 1.3 to 1.5. But we don't want it to work, for example, around 0.9 after, for example, a year of working, or like, I don't know, 200 hours of working. When you run with the high amounts of current, the battery voltage at the terminal drop much faster than the time when you use the battery with a smaller amount of current. Okay, so so far we talk about current, voltage. We also talk about battery and the voltage sources, and also the factors that impact the life of a battery. But here we are going to also talk about conductors and insulator. So usually any material that we have in this world, we can classify them in 3 classes. Either they are conductor, which means they can let the electricity to go through them. They are insulator, which means they don't let the electricity or current go through them. or they are semiconductor, which means depends on a specific condition, they can let the current go through it or do not let the current go through it. But usually as a main two category, we can say materials either are conductor or insulator. Conductor materials like copper, aluminum, iron, any or like water, sometimes they are like letting the current go through them. Insulator are like glasses, plastic, what else? Porcelain, ceramic. These are like the type of material that's, yes, wood is another insulator that they cannot let the current go through them. So there is a classification between different material that we have. For example, we have different type of materials that can be conductor, like silver, copper, gold, aluminum, nickel, iron, nichrome, or the other type of material that we have. But there is, if you want to classify them, that whether silver can let the current go better, or gold, or copper, or aluminum. If we want to have kind of index to know which one can let the current go through them much better, we define an index which is called relative conductivity. Relative conductivity for copper is 100. That's why make it a good conductor. Silver is much better than the copper, but because silver is very expensive and does not have those strengths that the copper wire have, we use the copper and aluminum more than the other material like silver or gold. But compared to the copper, aluminum relative conductivity is 61, or for example, for iron is 14. So you can have, with this index, you can have some sort of sense that how much this material can let the current go through it. For example, you know that the iron compared to the aluminum and compared to the copper is like material that does not let the current go through it that much. And if I'm gonna choose a material for a wire, I'll prefer to use copper. If copper not, I will go through the aluminum. I'm not using gold because gold is very expensive and does not have that strength that I need for a wire. So we talk about insulator, where insulator are coming to play a role. When we have this wire of a conductor and we want to do the transfer, or we want to kind of having a shield over them, or we want to kind of use them in different structure, but we don't want to touch these specific conductors because they're having currents, and if you touch them by mistakes, you will get shocked by electricity. That's why we use insulator. So for holding a wire, we use this insulator. If we want to bend the wire and we also want to hold it still, we use this type of insulator. So if we want to hold the wire, it's the time that we need insulator, and insulator are coming to play the role. Again, for the insulator, if we want to know how much, like, again, classify them and have kind of understanding for them, we define a term which is average breakdown strength, which means if I apply this much of voltage over this insulator, it is still working fine. If the voltage goes beyond this level, over the this, like over centimeter part of this insulator, then there will be a spark, or this one will damage. So up to a level of a voltage, if you apply voltage to this insulator, they work fine, nothing happened to them. But if you increase the voltage too much, you can break the insulator through the creating the pulse, and that's causing the damage to them, and they cannot work fine. So among these different type of insulator that is mentioned in here, as you will see, mica and glass has the high average breakdown voltage. It means when you apply 30 kilovolt voltage to the air starts to break down, ionize, and it's not going to work as an insulator anymore. Porcelain after 70 kilovolt voltage will be damaged. Rubber after 270 kilovolt voltage. Teflon after 600 kilovolt voltage that you apply. For the glasses, and even much better than the glasses, mica material, when you apply 2000 kilovolt voltage to them, then they will be damaged. That's why you will see in many cases they use mica for the insulator. And as I said, there is also a semiconductor, which semiconductor are type of material that depends on a specific amount of time. They can let the current go through them, or they kind of refuse to let the current go through them. So sometimes they act as a conductor, sometimes they act as an insulator. And the last topic for this chapter is the ammeter and voltmeter. So if we want to measure the voltage or the current of any equipment or any part of a circuit, we need to have sort of devices to measure the voltage and measure the current for us. So this is a kind of equipment that can measure the voltage for us. And as you will see, it has a little screen that you can read the amount of voltage. There is a selector that you can put the voltage in a specific range that you want. And then there is a terminal, positive and negative, that connected to a wire. And then from this alligator terminal, you can connect it to the part that you want to measure the voltage. And as you will see, voltmeter is connected in parallel. It means the positive point of voltmeter is connected to the positive part of a source or a element that you want. The negative part is connected to the negative part of the element or the source that you have, and then you can read the value in here. We also have devices that can do different tasks like voltage, current, ohm, and whatever. But here is the simplest one, which is considered as a voltmeter and can only measure the voltage. Similar to the voltmeter, we have devices that can measure the current. We call them ammeter. Ammeter connected in series. Similar to the voltmeter, ammeter has also screen, a selector for the range of the current, positive and the negative terminal. The positive is connected in here, and the negative part connected to the other side of the circuit. So if you want to measure the current of the wire in here, you have to break the wire, create an open path, and then connect the ammeter. So when you want to consider where or how to connect the ammeter, you usually should think that the amount of current, if it was going into this direction, now it needs to go through the ammeter and then coming back. So you have to open your circuit and then connect one side to here and connect the other side to the other port. So if you consider that here there was a wire, it's actually like you open this wire. Sorry. So if at the beginning there was a wire in here and this current was going through and you want to measure this current, you cannot bring it parallel. You have to open this current, take it out, and then connect one side to one of the paths and connect the other side to the other point. In this case, current goes through the ammeter ammeter will measure this current and then it's go back flow to the rest of the circuit. This type of ammeter and voltmeter that you saw are digital ammeter and voltmeter. You just connect them and the number is digitally appear in here. In past, we have ammeter, voltmeter, or ohm meter that they were analog. So there will be a pointer in here that depends on the amount, and there are some ports that based and also selectors that depends on the voltage or the ohm or the current that you're going to measure. You connect to these ports, and then these pointers are moving through this plate, and depends on what number that you have in here, you can read the number for the current, for the voltage, or for the ohm. As I said, we have digital multimeter that has both current, voltage, ohm, and some other factor depends on how advanced is the multimeter, and they can measure current, voltage, and ohm through one device. So you have ports in here, you just need to connect them. If you look more into here, it says for voltage, use this red one, and the green one in here. Let me point to them. You use this green one, red one, and this come for measuring the voltage. For measuring the current, if the current is around 400 milliampere, you will use this port and this one. If the current is around 1 ampere, it's not milliampere, you will use this port and this one to measure the current. Any question? If you don't have any question, you can have a 10-minute break.
Professor, so these multimeters also have continuity, which is also helpful, right? When you're trying to identify a circuit.
Yes, correct. Or if you want to see if there is any short circuit in your system, or if you want to make sure everything is connected, you can put a selector in a way that if there is no pass, it will start beeping. If it's short circuit and there is a pass, it's not. And you can figure it out that you build your circuit correctly and your circuit is complete.
Yeah, like for example, at work, because I work for a contractor, so when we have, problems with any circuits, we use continuity to see if there's a short or something happened to the wire.
Yeah.
So it's helpful to have the multimeter.
Yeah, it's very helpful if you want to troubleshooting something. It's very handy. As I said, these topic from the PowerPoint are from the book. So exactly the text is from the book, but if you think you want this PowerPoint, I can upload it and send it through the email. Just let me know in the chat section, but everything is from the book. You can have 10-minute break and we will meet in 7:25 again. Okay, let's start chapter 3. Just to make it clear, guys, chapter 2 is finished. So homework for chapter 2 is due next Monday. Also, if you didn't get the chance to submit your homework for chapter 1 today, you can also submit it for next Monday. So let's see what we are going to cover in this chapter. As the name says, it's mostly about the resistor. We are going to know in general about the resistor, then knowing about the physical characteristic of a resistor, like for example, how dimension, like area, length, or like stuff like that of a material can impact the value of the resistor. We also want to see how temperature can affect the resistor of a material. Like for example, when we increase the temperature or reduce the temperature, how the resistor is affected, whether it's increased or decreased. We also, so beside understanding the resistor, we're also going to learn about the reading the resistor, especially the color coding, the color coded one that has different colorful band over the resistor. We are going to learn how to read this type of resistor. And also we are going to learn about some other type of resistor that we have, not resistor, it's like a devices that work based on the resistor, like a thermistor, photoconductive cells, or varistor, and how they can control the resistor in the terminal can be controlled. So if we consider, usually we can consider this example, like if you have consider a pass and then some mountains, and then consider some mountain climbers. It's kind of a little childish example, but it's good to get some understanding of the resistance. So if this person want to go through this pass and there is some mountain, so what will happen if it's running through this pass? When it reaches to the resistor, it starts to moving much slower. The time that it takes to reach to here is smaller, and there is like a kind of opposition to the movement of this person, because it was moving on a direct path, but now there are mountains that it needs to go through. Similar things is for the resistor. Consider this climber is electron. Electrons prefer to move fast in a direct path, but if there are some mountain in between, they cannot go fast. They have to do it very small, and while they are going through this mountain, they sweat, they have heat. So this is what will happen in real world when we have a conductor and we want, or any material that electron go through it. Depends on the type of material. We have some opposition to flow of charge that we call this opposition resistor. This is the symbol that we use for the resistor. So if electron is going through the direct path, now that we have this resistor, it needs to go ups and down and go. So this is the symbol that we need for the resistor. And similarly, as we said, the opposition due to the primarily to collisions and the friction between the free electron and the other electrons, ions, and in the atom that the path has, then they can convert the supplied electrical energy into heat or the increasing the temperature of the material that electron go through it because of this resistor. So if you consider a heater, it's actually a big resistor inside it. And then the electron, when go to this resistor, they produce heat. And then you can use this heat in a form that like warm up your place. That's working based on the resistor. And the resistor that used in a heater is a high resistance material. So how we can consider if any material is a high resistance or low resistance, or what is the range? So usually the resistance of the material depends on the type of the material, depends on the length that you considering, depends on the cross-sectional area, and it depends on the temperature that the material is going to use there. So when the path is longer, as we expect, the path for electron to go through is become more longer. So the greater the resistor factor will be. And the free electron pass more easily through conductor with larger cross-sectional area. So if we have a larger space, they can move faster and more number of electrons can go through it. Also, the higher the temperature of a conductive material, the greater the internal vibrant and the motion of the component will be, and then it is difficult for a free electron to move through this material, because already there are a lot of electrons that are jumping up and down, and now there will be an electron that want to go from one point to another point, while in the atom there are some other electrons that moving ups and downs. So for this electron, it will be much harder to move from one point to another point. That's why the resistor also is increased with the temperature. So if you consider, so far we said that the lengths have impact. When the length is increased, temperature is increased. The cross-sectional area is a reverse impact. When the cross-sectional area increase, we have larger space for moving the electrons. We said temperature has a positive impact. When they increase the temperature, the resistor also increase. But we are going to talk about the material, how we can show the impact of a material if I want to draw a formula for it. So the material is coming based on the resistivity. So resistivity is a parameter that is defined based on the circular mile of a resistor per feet at 20 degrees Celsius. And as you will see for different conductive material that we talked in the previous chapter, we have also the resistivity factor in here. And when the resistivity increases, it means that this material have a higher resistance. So as you will see in here, copper has a smaller resistor than the other. That's why another reason that makes it a good material for conductor and using widely in this industry. And now it just shows you some comparison. For example, if you have a copper or an iron, because resistivity of the iron is more than the copper, then the resistor of the iron is more than the resistor of the copper. If the length of a copper, so the material, we have two pieces of wire, both of them are copper, so the material is the same, but cross-sectional area is also the same, but the length of this one is L1, the length of this one is L2, where L2 is much bigger than L1. So as we expect, when we increase the length, we have increase in the resistor, so R2 is more than R1. Now there is a comparison based on the cross-sectional area. We have R1, we have also R2, but as you will see, R1 has a greater cross-sectional area than R2. Therefore, the resistor of the R2 is bigger than the R1, because when you have cross-sectional area bigger, you can let the electron move easily. So there is less resistance. And then if you remember from the table when I was talking, I said the resistivity is based on the circular mile. And here is a definition. If you have, there is a kind of, this circular mile is used only for wire industry. And when you are working with the wire, this is the term that you are going to use. So for example, if you consider a piece of a cross-sectional area of a wire, that is located inside a square, or in other words, the diameter of this circle that you have in here is 1 mile. Then 1 mil, so you have one circular mil in here that is defined for this piece cross-sectional area. So when we say it's 2 mil, it means the area in here is 2 mil. And then if you want to consider the area before we use PR2 for measuring the area of a circle, but in order to get rid of this number of P and make it like a exact number, we use the diameter in mils power 2. So this is the difference between the area that we use in circular mills than the one that we have for like from geometry, that you use the cross-sectional area equal to PR2, where the R is the radius of a circle. So here for this piece of wire, if you have the diameter 2, then the cross-sectional area is 4. And for here, if you have the diameter 3, the cross-sectional area is 9. So whatever is the diameter, you just need to make it a square root and, make it power 2. And then you have the final answer. If the material that you are going to work is not circular, then you have to use the cross-sectional area regularly as you do before. The width multiplied by the length. So here, as we said, we have only this type of definition for the cross-sectional area for only when we are going to deal with the wire. So for the wire, we have a piece of paper, which is this one considered as American wire gauge. I don't know if I zoom, you can see it also as a zoom, but oops. Could you see it as a zoom? Yes or no?
No, Professor.
How about now? Okay, so I think everybody needs to zoom in through their screen. So if you zoom in through your screen, make this table visible to yourself, because I cannot do it for yourself. But let me bring the pointer so you could see what I'm talking about. So here, oops. Okay, so here it's like AVG, which is American wire gauge. These are the different sizes that we have for the wire. And these are the area of different wire. And these are the ohm per 1,000 feet at 20 degrees Celsius. And this is the maximum allowable current for that type. For example, I will say gauge number 4. Gauge number 4, you are coming in here. This is the gauge number. This is the area that you have for this wire. And this is the amount of resistor that you have for this wire per 1,000 feet. If it's 10 feet, you will multiply it. This one is over 1,000. So you have to do the relationship, say 0.2 for 1,000 feet, how much for 10 feet. For example, if I have 2,000 feet of a wire, and I'm going to find the total resistor of a wire with the gauge number 4. I just come to this row, see gauge number 4 has a 0.224, let's say, for 1,000 feet. So it's a 2,000 feet. So you will multiply this number by 2, and this will be your resistor. So instead of going through different type of calculation, converting numbers to each other, you just need to go through this table, find the number of the gauge, and then you can find the number of value of resistance. And here is different wire based on the table that you have. This is 0, 0. As you will see, we have couple of wires connected to each other, and then there is a shield over there that you have the diameter in here based on inch, which is 1/3 inch, the diameter of this piece of wire. You have 1/12 inch, you have 1/14 in here, sorry, 1/16 in here, and so on. So you, based on the different diameter that these wire have, they have different number. This one is number 28, which is used in the telephone. For example, number 22, which is used in radio or television. Number 12 and 14 used in lighting outlets and general home use. And number 0 is used in power distribution. So usually you go to this table, find the number, for example, number 12, which was used for home. I have it in here. The amount of resistor for it is 1.5 per 1,000 feet. If I have half a feet, 500 feet, I will make this resistor half. If I have 2,000 feet, I will multiply this value and we'll figure it out based on the length of the wire, how much resistor I have. And then we are going to see the temperature effect on the resistor, conductor, semiconductor, and insulator that we have in here. So if we have, when we increase the temperature, if the resistor increase, we call this type of material positive temperature coefficient. But if when you increase the temperature, the resistor of your material goes down, we call it negative temperature coefficient. So these are the type of coefficient that you can have for different material. And considered here, when I'm increasing the temperature for copper, as you will see in here, the resistor is increasing. And when I go to the other side, when I'm reducing the temperature, the resistor is also decreased until this specific point when the temperature is 0. This is negative 273, which is the 0 in the Kelvin. So in here, if you do some mathematics or geometry in here, you will see that there is a point, we call it infrared absolute 0. And in this temperature that we have in here is the temperature that we consider the value of resistor for it as a specific point that the value of the resistor is 0. So this one will help you later when you have some you want to do some sort of calculation for the impact of the temperature over the resistor. And then this value of infrared absolute temperature is, there is a table for it, and you can see it for different materials. And there is also a coefficient, which we call it alpha 20. If we go back to this graph in here, so if I have some sort of temperature going from 0 to T1, there is a change from resistor from this value to R1. Or in other words, if I go from T1 to T2, there is a raise in temperature from R1 to R2. So the slope in here is called alpha 20, that can be used as a coefficient for the temperature, and you will see in here for different material is given in this table. Let me see if I could bring one or two examples from the book, so we could get done some example in here, because I think everything up to here get more of a theory. I'm just uploading files, just bear with me. These are like my older slides. I'm gonna go through it. No, not this one, this one. So remember the graph that we just have in here, that when we have temperature T1 going to temperature T2, we have change in the resistor from R1 to R2. This is the formula that we have in order to find the value for the resistor in a second temperature, or if we have the value of resistor in the second temperature, we just want to figure it out what is the temperature. This is the formula that we are going to use. The value that you have in here is in the absolute value, in the absolute element. So this absolute T1 indicate the infrared absolute temperature. Again, let's go back to this graph to make sure we are correctly understanding. This is point T1, this is point T2, but there is a point in here which is called infrared absolute zero, which is shows also in absolute. So here this is absolute infrared zero, temperature 1, temperature 2, resistance value at the temperature 1, and resistor value at the temperature 2, and then you can put the value in here and find out the result. So let's do an example together in here. If the resistor of a copper wire is 50 ohm at 20 degrees Celsius, so R1 is 50 ohm, T1, first temperature is 20 Celsius. What is the resistance at 100 degrees Celsius? So T2 is given 100 degree, and we are going to find R2. But if you remember from this formula that we had in here, we have T1, we have R1, we have T2, we are looking for R2. We also need the absolute value for absolute infrared zero, that if you look at this table, it's given in here. This is for the copper wire. For other type of material, you have to go through this table and figure it out. So if you're in your homework, you'll have a question like this, and you need to have infrared absolute temperature. This table is also available in the book. Based on this table, you will just look what is your material and what is this absolute temperature. And then you will put it in this formula, which will be similar to this. And you know, this number is just positive. You don't need, because it's absolute value, you don't need to bring it as negative number. So this is the absolute value, temperature 1, resistor 1, temperature 2, and we are looking for resistor 2. Just a simple math, multiply this part by this part, as you will see in here, divide by this one, as you will see in here, and your resistor will be 65. So as you see, when increase the temperature from 20 to 100, my resistor increased from 50 to 65. So this one was the positive temperature coefficient. So when you increase the temperature, the resistor also increased. This is another example. If the resistor of a copper wire at freezing point, which is 0 degrees Celsius, is 30 ohm, what is the resistor at negative 40? So I have R1, T1, I have R1, I have T2, and I know the absolute infrared temperature. The same formula, just put T1 in here, R1 in here, T1 in here, R1 in here, T2 in here. But look, because it's negative, you will also enter the value in negative. And then we are looking for R2. Simple math in here, and then you will find the value for R2. Another small, yes. Yes, Stephen? I told you it's an infrared absolute temperature in here, because if I want to do, for example, if I want to write a relationship between R1 T1 and R2 T2, I also need a point that this line that's coming connect R1 and R2. This is the dashed line that connect R1, R2. If I continue, there should be a point that is also intersect with the temperature one. So I need to know what is this point in order to reach to this formula that we have. So the formula that we had in here, we need to know that intersection. Now let me see what you said in here. Yes. kind of point when these are shifting to kind of zero value. Okay. Let me see. Okay, another type of example that we also have, I think I don't cover that one also in my previous slide, was it's good to have some example about it because it can be a good question for your when you are doing the homework, is that the formula for the resistor based on the length, based on the cross-sectional area, and the type of material that is used is this formula. Resistor is equal to rho, which is the resistivity of a material, L, which is the length of a material, and A, which is the cross-sectional area. In circular mill, if you use it in a circular mill, make sure that your resistivity also in a circular mill ohm per feet. If you're using meter for this, the cross-sectional area, you use it meter square. Make sure this cross-section, this resistivity also based on meter square. But because in this course, we usually work with the wire, they are circular. And as I said, if you want to go through the table, it's better to work with the circular mill. That's why we have cross-sectional area in this format and resistivity in this format. Let's have an example in here. So find the resistance of a 650 feet number 8 copper wire at a temperature of 20. So remember that table that we were discussing in here. We have to go to that table and find the number 8 value, the number 8 wire, and see what is the value of the resistor per 1,000 feet. So if I go to this table, this is number 8. And I see in here that the resistor per 1,000 feet is 0.6282. So I will write it down as a kind of given number. So this number is given, but as I said, this is for 1,000 feet. But here it asks you about 650 feet. So in order to do the math, you just need to multiply 650 by this number. So whatever number that you have from the table, just multiply it by the length of the wire that you have, and you will find the value for the resistor much faster. So if we don't want to use the table, let me see if I have any example in here. I think I have it in here. So this is an example. If we want to calculate the resistor without the table, just directly by calculating the area, the length, and the resistivity of the material. So it says kind of the number of, let me see if I have it in here. Yeah. For example, it says for the resistor of 100 feet length of a copper wire with a diameter of 0.02 inch at 20 degrees Celsius. So first you have to convert inch to mile, and each, as you will see in here, each mile is 1,000 inch. So if you convert this number from inch to mile, to mil is 20 mil. And then if you want to find the cross-sectional area, as we said, you just need to have the diameter multiply power 2. So 20 power 2 is 400. Now you have the cross-sectional area. The formula that we had for the resistor is resistivity multiplied by length divided by the cross-sectional area. The resistivity is given because it's a copper wire. You will go to the table for the resistivity. It's this table. You will see what is the value for the copper. It's 10.783. So you have this value, 10.73. You have the cross-sectional area 400, and you can find the value for the resistor using this formula. So resistivity, length is given 100 feet, and the cross-sectional area, which is 400. And then you can calculate the resistance. Just be careful when you have a kind of question like this. Make sure the length of a wire is in feet. You usually, resistivity is given to you. And then based on the resistivity unit, you can make sure that everything is in the correct unit. So the length should be in feet. The cross-sectional area should be in circular mil. Here it's given in inch. So you have to convert this number to mil and then find the cross-sectional area. And then it's when you do the math in here, it's a simple formula. You just put the number in here and you can find the value for the resistor. Let me see if I have another example. So we did also this example with also that temperature coefficient that we discussed. There is also a formula in here that you can find the value of resistor based on this temperature coefficient. And this temperature coefficient is defined based on 1 over absolute temperature plus 20, because we define everything in a base as a 20 degrees Celsius. And then the formula that you will have will be like this. Any resistor at any temperature will be the resistor at 20 degree temperature multiplied by 1 plus the coefficient in the temperature that you want minus 20. If you also do the math and coming into here, we can say that alpha 20 is equal to change in the resistor divided by the change in the temperature, and then divided by R20, which is the resistor at 20 degrees Celsius. So alpha 20 either is given or you can find it based on this formula. You know the change in the resistor, you know the change in the temperature, and you know the resistor at 20 degree. Then you can find what is the value of alpha coefficient. But usually is that alpha 20 is given. You have the resistor as room temperature. Any temperature it will be given to you, and you need to find the resistor. So alpha 20 for different material is given in here, a table based on different material and the different value for alpha 20 that you have. The other topic that we have is the change of the resistor based on the part per million per degree Celsius is also another form of saying change in the temperature that, for example, if we consider a 500 ppm, which is part per million per degree Celsius, is considered high, and 20 ppm, we consider it as a low. For example, 100 ppm characteristic reveals that if you have a 1 degree change in temperature, the change in the resistor is 1000 ppm or 1000 divided by a million. So it can say, if you do the math in here, is 1 over 1000. So when you change the temperature 1 degree, the amount of change that I have in the resistor is 1 over 1000. So whatever was the value before, now 1 over 1000 is added to the temperature, to the resistor. So all these things, either ppm per degree Celsius, alpha 20, or the absolute infrared temperature, all these things is a kind of way just to figure it out what is the change in the resistor based on the change in the temperature. So in some case, if we wanna just always like working with this formula or this formula, it just make it hard. That's why they have this ppm per degree Celsius. So if 1 degree you are increasing, I want to know how many, what is the relation for change in the resistor. So if I have now changed my temperature from 20 to 40, I know I have 20-degree change in a temperature, and I just need to multiply it by the number of ppm. For example, if my ppm is 20, I will multiply 20 by 20 degree divided by a million, because it's a part per million, and then I will find the answer. So this is what I mentioned right now. The change in the resistor, if you want to find out what is the change in your resistor, your nominal resistor, multiply by ppm, divided by a million, and multiply by the change in your temperature. Then you can find what is the change in the temperature when you create a change in, what is the change in resistor when you create a change in temperature. I know it sounds a little sophisticated, but believe me, when you start doing the example, you will figure it out very fast, and all these topics are very easy. Okay, let's consider this example. It says for a 1 kilo ohm carbon composition resistor. So I know that the nominal resistor is 1 kilo ohm with a ppm of 2500. So my ppm for this resistor is 2500, which means if I have 1 degree change in a temperature, the change in the resistor will be this number divided by a million. And now I want to determine the resistor at 60 degrees. Excuse me. Just give me a minute. Sorry, guys. So here, just the point that you have to pay attention here, it says determine the resistor at 60 degrees. It give us the second temperature, and it asks us about the exact value of resistor. It doesn't ask us about the change in the resistor. With the formula that we just talked about, we know the change in the resistor, but later if we want to know the resistor, the exact value of the resistor at this temperature, we need to add this change to the nominal value of the resistor. So let's calculate first the change in the resistor. So it's 1 kilo ohm, so it's 1000 ohm actually, 2500 ppm divided by a million, and then I have to figure it out change in a temperature. This number is given in 20 degree, and the second temperature is 60. So the change in the temperature is 40 degree, and the change in the resistor will be 100. Now I have to add the change in the resistor to the nominal value in order to find the exact value at this temperature. So my nominal value was 1000, the change is 100, so the total value is 1100 ohm. Is it clear? Any question? Okay, the last topic for today, which we also continue it on Thursday when we have, on Wednesday when we have lab, is type of the resistor. So for the type of the resistor, we classify them into two categories, which is the fixed resistor and the variable resistor. In the fixed resistor, we have the value of resistor in a fixed format. The value always is one value, but there is also another type of resistor, which is the variable resistor. This variable resistor can give you different value for the resistor, depends on the condition that they have or the type of structure that you have. You can access to different value of resistor. So the type of fixed resistor, one of them is a film resistor, as that you will see in here. And these are like the type of example that they have. This one is a fixed composition resistor, and this is the structure that you will see. So as you will see, there are some color band on top of this resistor, and then we are going to learn how to read this color band. These are the same fixed resistor with the color band, but you will see they have different sizes. When their size is bigger, they can have more power. It means when you have a bigger resistor, they can handle more current, and they usually not burn when you use them. But if you use, for example, this small resistor instead of this one and apply this 5 watts current and voltage into it, it will burn out very fast. So it's important when you're choosing the resistor, you make sure that this resistor is suitable for the amount of voltage and the current that you have. So these are different type of fixed resistor that we have in the industry. You can later in the book look at them, learn more about them, different structure that they have, different shape that they have. And then the second type of the resistor that we are going to discuss are the variable resistor. The variable resistor, also known as a potentiometer and rheostat. As you will see in this figure, there will be a knob or a control port that you can tell between any port A or B or C how many resistor you can have. So by moving this arrow, which can be a knob that move this arrow in here, you can determine what value of resistor to be located between A and B, and what value of resistor located between B and C. For example, as you will see between point A and this arrow, I have resistor RAB. Between this point and B, I have another resistor, which is a resistor, if we consider this point B, it will be BC resistor. And when you move the arrow, you can reduce the RAB and increase the resistor between B and C, or in reverse. If you move it this way, the share for the RAB will be increased and the share for the BC will reduce. So the actual view of a molded composition type potentiometer is shown in here. These are the ports A, B, C that you see in the previous slide, and this one is a rotating shaft or the knob that you can change this one. By changing this one and rotating this one, you're actually changing the position of the arrow, and then you can have different value between A and B and B and C. But the point which also you may notice is that the entire value of the resistor between point A and C is always constant. It's only between A and B and C that is different. So here also show this concept with using the ohm meter. Ohm meter, similar to voltmeter and ammeter, is a kind of device that can measure the ohm or the resistor of a component. It has a monitor, it has a selector and ports for connecting to terminal of the element. So when you put it between A and B, it's 1 mega ohm resistor. But if you use 2 ohm meter and try to measure the resistor between point A and B and point B and C, you will see 0.75 is between B and C, and 0.25 mega ohm is between A and B. But the point is, combination of the resistor between A and B and the resistor between the point B and C, if you add up these two numbers, is equal to the total number of resistor that you can read between point A and C. So it's point B that can be moved and change the share of these resistors. And these are different type of variable resistor that you have in here. Again, when you have different value of the resistor, if you apply a specific voltage on the entire ports A and C, then you can access the different value of the voltage between point AB and BC, because we have different amount of resistor, different amount of current will be in different amounts of voltage we will have in here, and different amount of voltage in here. So the next topic that we are going to discuss is the color coding and the standard resistor value, which I gonna continue this topic on Wednesday when we have the lab section. And in the lab section, actually, you have to measure some of these resistors. Any question?
Yeah, Professor.
Yes.
So next class we're heading in homework number 2, right?
Yes. Chapter 3 is
And
not
then-
finished.
Okay, and then next week we hand in homework number 1.
If you have homework 1 ready, you can submit it today. If you don't have it, next Monday, when we come to the class, you have to submit. Actually, next Monday is holiday.
Yeah, we don't have a class Monday.
So the next Monday that we will meet, I don't know, it's 23rd or whatever. So next time we are going for the Monday. So usually is Monday is for the lecture, Wednesday is for the lab. Next Monday that we will meet, you have to submit homework for chapter 1 and 2. And on Wednesday, we just have the lab. So this Wednesday, usually in the lab section, I do some lecture, which is similar to what we've done on Monday. And then you will do a lab for that one. We also, if we have some extra time, we also do some like, I will solve some question for you. If you have any question for homework, you can ask and stuff like that. So this upcoming Wednesday, I'm gonna continue this lecture because this lecture is actually the kind of definition for doing the lab. So you will receive bunch of color-coded resistor, and you have to determine what is the value. Because today we are ran out of time, instead of saying it here and repeat it on Wednesday, I will do it one time on Wednesday, and you will get to know what is the topic. Also do some example, which is like 6 to 8 resistor. You have to find out what is the value. I will do 1-2 example, and then you will do the rest on your own. That will be your lab. When we had actual lab, we give you actual resistor. But here, because we are doing it online, you get a picture of resistor. Clear?
Yes, thank you very much.
You're welcome. No homework is always due Monday. Whenever we have Monday class, you have to make sure that if a chapter is finished, you have to submit the homework, okay? Homework always due Monday. Okay, I
Professor,
will.
will these slides be on Blackboard? Just
Yes, I will send you the slide. Let me just.
will you always
I can
provide
do
the
it.
slides, or?
I can do it, but just remind me, okay?
Okay, yeah, that's good.
Let me do it now before I forgot it. Yes. Where? Could you share your screen and let me see who is talking? Steven, is that you?
No, that's
Hano, is that you? Okay, so I think you can now share your slide so I could see. Do you have it on a screen? Share your screen. No, not camera. Do you know where to share your screen? Oh, you are with the phone or the tablet. Okay. So let me find the book and just give me. Yes, but it's very small. Okay, I got it. So where is the question? No, they start next to it is not a important things. No. If it's in the table, you have to do it. Okay. Guys, any question?
I have a question. Did you receive my email?
When did you send the email? What's your email?
At like 7:51. lpaulino004@citymail.cuny.edu.
Let me write it. Oh, Palino. Just give me.
It was about me turning in the wrong PDF. So I needed to do it again.
Okay, for homework?
Yeah, for homework 1, I turned in the wrong PDF. So I was wondering if I could get a second try.
Yeah. Until next Monday, you can do it.
a chance to resubmit?
I don't know if I could cancel that submission, but have it ready. If you couldn't submit it, email it to me. I don't know why I didn't receive your email. I'm gonna check with the IT department because there should be an issue with my email because other student also said we sent you email, but I didn't receive. I also didn't receive yours. One of you also sent me an email at the beginning of the class. So there should be a little issue with my email. I'm gonna check it and then you can submit it through the email if the Blackboard does not let you to resubmit it.
Alrighty.
Professor, can you just confirm that you received my assignment for today? 'Cause I had just submitted it. Well, not
If
just now,
you
but like before
submit it
class
through
through Blackboard.
if you submit it through the Blackboard, is there?
All right.
So if you don't have any question, you are good to go for tonight and have a good night.
Professor,
Yes.
is only chapter 2 and chapter 3 due for next week?
Yes.
Okay, thank you.
Thank you, Professor. Good night.
You're welcome. Good night.
Professor, I just
Yes.
you see my email, I just typed it in, so